Let's try to understand the reason behind the statement, which reads the total potential difference across the combination of resistors in series. So let me have three resistors first. Three need not be three. It can be any number of resistors. And the total potential difference across all of it. So this is the total potential difference across all of it is equal to sum of potential difference across individual resistors. If this is the individual resistor, the sum of it will be equal to the total voltage. So let's try to reason it out. Why is it so? So I have the surface of the earth. So from the ground, I'm trying to reach to point C. I can do it two ways. One, directly lift the object from G to C, or I can take breaks. I go from G to A, then A to B, and B to C. So I'm doing a work of W1, W2, and W3 in shifting at different phases. And W is the total amount of work I did from lifting this 1 kg weight from G to C. So if say I'm doing an ideal work, that is, I'm not losing any kind of energy with anything else, no body heat, nothing, I'm just lifting it. Say I'm able to jump or fly or whatever this is, or carry it, I have stairs over there. So whatever it might be, the point is I'm just carrying it and all my energy is being spent in lifting it up. So the thing is, we can tell as per the law of conservation of energy that sum of the total work that I did in carrying it from G to C will be equal to sum of the individual works I'm doing over here. Right? It makes sense because work and energy are kind of linked, and the total amount of energy we spend can be broken up into chunks. It makes sense, right? So on a similar line, if we can reason over here, I have a positive charge touching the negative charge. I'm calling that as G. I want to carry it to point C. I can do either by lifting directly or individually. Say I'm carrying a 1 coulomb charge. So Q is equal to 1. So our formula becomes V is equal to W. So can I tell the potential difference from G to C is V, and V is equal to W, sorry. Can I tell the total potential difference from G to C? The potential difference from between G and C is W. Potential difference across AG is W1, W2, and W3. So now what can we conclude? V is equal to V1 plus V2 plus V3. Right? All we did was substitute it over here. Right? Because the total energy we spend is equal to sum of individual energy we spend in between. And that's what this statement is talking about. Right? So in terms of electric world, we talk of spending energy and charges and everything in terms of voltage. End of it, it's the same thing. It's about work. It's about spending energy. It's about energy, is it not? Energy on a single coulomb of charge. That's all we talk about. Right? That's your voltage. Right? In this world of charges and everything, voltage makes sense. Voltage is the language which we talk. That's all, nothing else. It's the same idea, that's it. Right? Makes sense? So total work is equal to individual work. Total voltage is equal to individual voltage across the ends.